suppose one comment that would be fair to make is this is an introductory text at undergraduate level to principles of quantum mechanics, and this is the last chapter, and this is the last part of towards the very end of the last chapter. So in flying over the icebergs, he's Davies and Betts giving you a taste of what's to come, and it's probably not surprising that what they're presenting now is somewhat harder, because you're moving towards grad level and not spelling things out, just glossing over things to some extent. Anyway, that's the feeling that I'm getting from what's being presented now. All right. So last session we were talking about the idea of using a density of final states. We called it rho. So we had so instead of summing over the AM squareds, when you're interested in the probability of getting into a particular final state, and you get all these contributions from various initial perturbing frequencies, let's say, so you're summing sigma of AM squared. Well, when the interval between those frequencies is small, then you can approximate your sum by an integral, and hence you can start using a density function. Now, so we had an expression, instead of summing sigma AM squared, you had an integral, and you can't see it in the previous session, I'm just reading it off to you now. So that sigma AM squared then gets approximated by an integral over a range minus infinity to infinity AM squared rho, and there's your density function, rho of omega d omega. Okay, now that A of m squared, remember, that was your probability of a transition to state m. It was sharply peaked, remember, the sine squared form. So it was sharply peaked at the value omega mk, that particular angular frequency. So because it's so sharply peaked, then your rho, your density, and the matrix element h bar, the bar over the h mk, and those appear in the the h bar that appears in the AM squared. Remember, AM squared is the probability of a transition to state m, and h bar appeared in that term. So now we can get onto this session. So the density rho and the h bar, those two terms vary much more slowly than the AM squared, which peaks peaks strongly. So so these h bar and the rho, they appeared inside the integral before, and this is your m squared, AM squared. So because they're changing so much more slowly than the AM squared, which peaks, so you can approximate. You can bring them outside the integral, and where this omega here, you can approximate it just as omega mk. Right? You can put this value here, because they're not going to change much as your omega moves away from the value omega mk, because this term here peaks so strongly at when omega equals omega mk. Right? So these two terms you can take outside. They're effectively constant over because this peaks so much over this range. Now, so your h bar and omega that were inside the integral, you can take outside, because they're effectively constant. over this effective range, because this is effectively zero outside. Once your omega starts getting outside this range, right? Now, what is this? It's effectively the area under the peak. If you look at it, right? So it's the area of your peak graph, the area under the graph of your peak term, your AM squared. Now, how to actually integrate this? That's not explained. At this stage now in the text, there's a lot of stuff just getting thrown at you, which I suppose is understandable, given that it is an introductory text, and this is towards the end of the book, the end of the course. So I'm just wondering. It seems you can put a homework question mark. So this and this is just here. So you get a T coming out of it. Now, can we approximate this? Is it just simply? Are we just saying this is effectively what did we say before? T squared over 4. Is it as trivial as that? Or is using perhaps the complex function integration, contour, what's called contour integration from complex variable theory to solve this? I'm not sure. I mean, you can approximate it, right? This when this is small, sine of x is just approximately x. So we've done this before verbally in an earlier session. It was effectively just t squared over 4. So if you integrate t squared over 4, not so obvious. Anyway, you could try integrating that using complex variables if you know how to do that. But we're giving a whole course on complex analysis, complex function theory, sometime within the coming year. Okay. All right. So you end up with this. So what is this? It's the summing, or in fact the integration, of all your contributions AM squared. It's the sum of the probabilities that you end up in where your final state is UM in energy level EM. Right? It's the sigma, or in fact the integral, of your AM squareds, and those AM squareds with the probability of ending up of a transition to M. But if you have many ways you can get to that state UM, then you add those probabilities, right? So this is what you end up with over time t. Now, the couple of sessions back, we had a heading, the energy time uncertainty principle, and two things. And the second one was the so-called Fermi. Enrico Fermi, Italian-American nuclear physicist, Fermi's golden rule. So finally, we get to do that. Now, this is your probability of getting to final state UM, where the interaction time is t, from 0 to t, in effect. So we can talk about a transition rate. So if we divide this by t, that would give us a rate